So right there, I'm streaming. There's a link on the Piazza for the live stream. So, and it's being recorded right now. So, all right. Yeah, so if you can't see in the back, you can follow the live stream. Again, links on the Piazza. So what am I trying to do today? This is a goal. So I have the 3 first midterms from last semester. And what we're going to do is we're just going to work through every single one of them today. So that's going to be the plan. So the order will be this. I'll cover Davi Maximos first, and I'll cover Bharathwaj, Palvannan, and then I'll cover McGrath's last midterm. So we will actually be getting the answers to McGrath's midterm. If you already did it and you don't need the answers, you can leave then. But these first 2 you probably haven't seen before, so that's going to be the plan. Okay, before we start, do we have any last administrative questions? Anything administrative about the exam? Where is the exam? What time is the exam? No cheat sheet on the exam? Yeah. Okay. Yeah, that's the big one. So just keep in mind that we're not going to have a cheat sheet on the exam. It's going to be, for those of you that took 114E, it's like fairly standard. For those of you that took regular 114, probably not standard. It is what it is. All right, let's see. Pull it up. Okay. Any questions? Yeah. Is this also going to be available like after the live stream? Yeah, I'm recording it right now. Yeah, so I'll upload it to my YouTube channel after it's done. It'll take like an hour and a half, 2 hours before it's like ready, but it'll be up there tonight. All right, so yeah, first thing we're gonna cover then is gonna be Dabe Maximum midterm 1 from fall 2018. All right, this is from last semester. So again, this is just to give you an idea of what you'll see on a midterm, besides the one that McGrath wrote. So problem 1 almost is always an easy problem. So this first one is just to find the inverse of this 3x3 matrix, which is 2, 1, negative 1, 0, 2, negative 1, and negative 1, negative 1, 1. Okay? And at this point, we should know how to find an inverse. It's not something terribly hard to have memorized. Right? Put the matrix you want to invert on the left-hand side, and then put the identity matrix on the right-hand side of an augment, and then we just row reduce, okay? So row reducing, what are we going to get? So let's see. I'll swap row 3 up here, and then I'm going to also multiply it by negative 1. So we're going to get 1, 1, negative 1, and then 0, 0, negative 1. All right. And then since I can switch the other rows as well, it doesn't really matter. So I'll just write 2. Well, okay. Now let's keep it this way. 0, 2, negative 1, 0, 1, 0. 2, 1, negative 1, 1, 0, 0. Okay, reduce, 0 out this guy. And on the exam, you don't have to write like what row operation you're doing. You can just write this like squiggly mark, and we should be able to figure it out. As long as you didn't do anything like super legal, of course. So this is really row 3 replaced with row 3 minus 2 times row 1. And so now this is 1, 1, negative 1, 0, 0, negative 1. Okay, 0, 2, negative 1, 0, 1, 0. And then this is 0, negative 1, 1, and 1, 0, 2. Okay. More reducing. So now let's get 1, 1, negative 1, 0, 0, negative 1. I'm going to switch these 2 rows and take a minus sign of that last row. So you get 0, 1, negative 1, negative 1, 0, 2. And then down here, you have 0, 2, negative 1, 0, 1, 0. All right. I'll just walk through the row reduction now. 0, 0, you get a 1, and this becomes 2, 1, 4. All right, and that's by zeroing out this guy. And then now what? 1, 1, 0, 2, 1, 3, 0, 1, 0, 1, 1, 2, 0, 0, 1, 2, 1, 4. And we get the idea. Okay, eventually we get then, you get the identity here, and you get 1, 0, 1, 1, 1, 2, 2, 1, 4. So this is the inverse. Okay, any questions on the inverse? All right, and then part B asks the following. Solve the system of linear equations, and you get 2x plus y minus z equals 1, 2y minus z equals 2, and negative x minus y plus z equals 3. How do we solve the system? Any ideas? Okay, so we can plug it into matrix, and if we do so, we get the following, right? 2, 1, negative 1, 1, 0, 2, negative 1, negative 1, negative 1, 1, 3. But, okay, does this look familiar at all? Yeah, the left is the one we just found the inverse of, right? So the left matrix is 2, 1, negative 1, 0, 2, negative 1, negative 1, 1, 1. Here you go. This left guy is the exact same thing we just found the inverse of. So what can we do to find the solution to the system? Yeah, multiply the inverse with the b vector. So, right, if you have ax is equal to b, then x is equal to a inverse times b. And in our case, a inverse we found above is 1, 0, 1, 1, 1, 2, 2, 1, 4. Your b vector is going to be the 1, 2, 3 vector, right, and that's going to equal x. And so if you multiply that out, what do you get? You get 4. 1 plus 2 plus 6 is 9. And then 2 plus 2 plus 12 is 16. Okay? Any questions? All right, number 2 is find the determinant. All right, and it's the following matrix. 2, 1, negative 1, 1, 0, 2, negative 1, 0, negative 1, negative 1, 1, 0, 1, 0, 0, 1. Okay, and what's pretty much the best way to find determinants in this class? Row reduction, yeah, that works. I actually think, yeah, the expansion isn't that bad, right? So both work. Let's do the expansion method. So where should I expand? Bottom row or last column. Yeah, bottom row or last column. So what we're going to do is we're going to expand along this row. Okay. So how do you do that? Well, there's really only two. There's only really two determinants you need to worry about, right? You take the 1 down here, okay, and then you get negative. You get 1 times negative 1 raised to the 4 plus 1. All right, times the determinant then of 1, negative 1, 1, 2, negative 1, 0, negative 1, 1, 0, right? Because that's the rest. Okay, and then you add to that. Now, you don't need to expand along the zeros because they're just going to be 0 times something. So now expand along the last guy, and you add 1 times negative 1 raised to the 4 plus 4. Since that's in the 4, 4 entry. And now you get 2, 1, negative 1, 0, 2, negative 1, negative 1, negative 1, 1. Okay. So now what? And it is. All right. So this determinant is actually, we actually like kind of row reduce that matrix up here. If you realize that and you can follow what row reduction steps you did, you can actually just find the determinant, like considering which row operations you did, right? Does everyone see that? Like this matrix, 2, 1, negative 1, 0, 2, negative 1, is just this matrix. And then we essentially did row operations on this matrix, right? To get it into like a triangular matrix. So if you just like follow which like steps you did, you can find the determinant that way, or you can just calculate it. That's fine. Anyways, so now I'm going to cofactor expand along the last. Whoops, that's the wrong column. I'm going to cofactor expand this guy up here in this matrix. So I get 1 times -1, right? -1 raised to the 5. And then here now I get another 1 times -1 raised to the 1 plus 3. And then that's multiplied by the determinant of 2, -1, -1, 1. All right, and now I add, this is just 1, right? Because this is a positive 1, this is a positive 1, so you just get 1 times, and now where do we want to expand? Well, I guess we can cofactor expand along this guy. So you'll get then 2 times -1 raised to the 1 plus 1 times 2, -1, -1, 1 plus, and now we have to cofactor expand the bottom guy, -1 times -1 raised to the 3 plus 1, and then what's this entry up here? I erased it. Oh, it's a 1. Okay, and so now this is 1, -1, 2, -1. Okay, so this is a -1 times, this is a positive 1. The determinant of this guy on the inside is 2 minus 1, so that's just 1. And then you add to that 1 times, well, so that's just a 1, and then this is -1 squared, that's a positive 1. So 2 times 1, and then add to that, this is -1 times a positive 1, so this is a -1. So minus 1 times the determinant of this guy, -1 plus 2, so that's a positive 1. Right, so there's a -1 plus 2 minus 1, -1 plus 1, and so you get the determinant 0. Yeah.
Wait, so are you just doing the like -1 to the I plus j instead of doing like the plus?
Minus, yeah, exactly. So I know like I know Jachun does this like plus minus, like for the first row and stuff like that, and then like minus, plus, minus. Yeah, I'm doing this instead of writing out the plus minuses, but you can use whatever you want. Okay, any questions? Standard determinant problem. If you don't get 0 on this problem, I remember we just took half credit if you made any kind of calculation error. So like really just check any determinants you have to take, because that's the entire point, is to like be able to compute what's going on. All right, even though computers can do this, you might as well learn how to do it by hand, I guess. All right. Next problem, number 3. Problem 3. All right, problem 3 is the following. Part A asks, are the following vectors in R3 linearly independent? All right, and you got V1 is equal to 1, 1, 0. V2 is equal to 1, 0, 1. And V3 is equal to 0, 1, 1. Okay, what's the definition of linear independence? Yeah.
A linear combination of them equals 0, then all the coefficients must be 0.
Yeah, so if I do C1, V1 plus C2, V2 plus C3, V3 equals the 0 vector, I want these guys to only be 0. All right. So we set up a system of equations, really, and then so you get C1 times 1, 1, 0 plus C2 times 1, 0, 1 plus C3 times 0, 1, 1, right? And that's equal to 0 vector. Okay, so now you have your system of equations put into a row augmented matrix, 1, 1, 0, 1, 0, 1, 0, 1, 1, right? And that's really just 0 on the right-hand side, so you don't even have to write it. So what are we looking for in this augmented matrix here? Or in at least this coefficient matrix part? Let's call that A. Yeah, so we can check if it's invertible, right? Since that A matrix is square. So if the determinant then is non-zero, what does that say? Well, determinant non-zero tells us that it's going to be full rank, right, as a square matrix, which means the number of, the rank of the matrix is equal to the number of the columns, which means that the only solution to the homogeneous system is going to be trivial, right? So that's what the determinant tells us. So just find the determinant. What is determinant A? And so you'll get, we can do row reduction this time. 1, 1, 0, 1, 0, 1, 0, 1, 1. What does this become? 1, 1, 0, 0, negative 1, 1, 0, 1, 1, 1, 1, 0, 0, negative 1, 1, 0, 0, 2. Okay, and so this determinant, right, only thing I did was add and subtract multiples of rows from each other, so the determinant's unaffected. Okay? And that way, all we have to do is multiply diagonal when the determinant's equal to negative 2, which is not 0. So therefore, the columns v1, v2, v3 are linearly independent. Yeah?
Also, if you just, does it also work that if like on the bottom row or whatever row, you have like just one thing, like one element, and it, obviously the other side's 0, so if you get like a number equals 0.
Not quite, because what if, so what if I had some, so this is a hypothetical, but what if I had some matrix that looked like this? So it's longer than it is tall, right? And then I have like 0, 0, 0, 3, 0, 0, 0, right? Well, the bottom only has one thing, but now you have like 4 free variables here, right? So you're asking me if the bottom only has one entry, right? No, that doesn't work, right? Because you want the rank of the matrix to equal the number of columns in order to get the only the trivial solution to the homogeneous system. Yeah.
Okay.
Can you explain again why, if the determinant isn't 0, that means that it's linearly independent?
So if the determinant isn't okay, yeah. All right. So there's like a bunch of equivalent definitions of like rank and determinant and stuff like that. So one of them is if the determinant is non-zero. Okay, so determinant not equal to 0, then the rank of your matrix is going to equal the number of rows and the number of columns. Okay, and that's for a square matrix.
Okay.
So for an n by n matrix, if the determinant's non-zero, the rank is then n, right? So if you think about it, that means what is the rank? The rank is the number of non-zero rows in row echelon form, right? So if you reduce a square matrix into row echelon form, and its full rank.
Oh, then there's no rows of 0.
Yeah, there's no rows of zeros, exactly. So it's going to be linear, yeah.
Can we also solve this question by saying that the matrix has a pivot in each row?
Yeah.
We don't
Yeah.
calculation.
You don't have to do the determinant calculation. If you row reduce it into that triangular matrix right there, yeah, and then you say each well, you can't, you have to say that rank is equal to 3 is equal to the number of columns. Like, that's the proper justification, yeah.
What if it like wasn't a square matrix? Like how would you know what to tell?
Rank equals pivots, rank is equal to the number of columns. Right? Because rank is equal to the number of columns means that you're not going to have a free variable.
So like if there are more columns than rows, then you automatically know it's not.
Yeah, exactly. Yeah. That's actually a big tell, right? If there are more columns than there are rows, you're like you automatically don't have linear independence. Okay. Any other questions? That's just part A. Okay, let's erase that. Part B is find a value of t that makes the vectors in R3 linearly dependent. All right, not independent anymore, but dependent. So now you get v1 is equal to 1, 1, 0. v2 is equal to 1, 0, 1. And now v3 is equal to 0, 1, t. All right, so now we need to find a value of t that makes the three vectors dependent on each other. Okay, so what's the idea? Well, in part A, we wanted the determinant to be non-zero, right? But what do we want in part B? Yeah, we want the determinant to actually equal 0. So what do we have now? So now linear dependent would mean, well, okay, so if we wrote out this system of equations, it's literally the same thing, except there's like a k there instead of a 1, right? So it's the same thing. You have the same coefficient matrix, that's just the k. So so this is our coefficient matrix, 1, 1, 0, 1, 0, 1, 0, 1, or t, just whatever parameter you want it to be, right? So now we want to find the determinant of this matrix, and we want that to equal 0. Okay? How can we do this? Well, we can actually just do row reduction with the parameter. So, okay, let's have the determinant brackets. If we reduce 1, 1, 0, 0, negative 1, 1, 0, 1, t, and then if we reduce again 1, 1, 0, 0, negative 1, 1, and then 0, 0, this would be t plus 1. Okay, so how do we get this determinant to be 0 then? Yeah, t equals negative 1, right? If this entry is 0, then we're done. So t plus 1 equals 0. And so that means t is equal to negative 1. Okay, you could have done the cofactor expansion for the determinant, whatever. I just did row reduction here. Any questions about linear independence type problems? All right, so usually what will happen is, yeah, they'll give you like, so this is an R3, right? And R3 is a 3-dimensional vector space, okay? If they give you 3 vectors in a 3-dimensional vector space, you can always use like the determinant method of finding linear independence. Again, just write out that system of equations, form your coefficient matrix, and again, don't take a determinant of a non-square matrix because you're just going to get a 0 on the problem. So just write things that make sense, I guess. All right, let's move on. Problem 4. 10 true-false problems. Okay. You guys aren't going to have 10. You guys aren't going to have 10. But these didn't require justification. Your problems will require justification. So that's the trade-off. Yeah.
If our justification is pretty sound, but we get it wrong, is that like half credit or?
We'll figure it out once we get down to it. Once we like actually grade it. I mean, it's a really like a case-by-case kind of thing.
Okay.
Yeah, I don't know. Like if you get it wrong, like for example, if you say false, but it's because you took a determinant, you made like a calculation error on the determinant. It's like, oh, are these vectors linearly independent, true or false, right? And it's like, I give you some vectors, you take a determinant, there's a calculation error, and then for some reason you say it's true, they're linearly independent, right? When it's supposed to be false, then we might like give you a point because like you knew what to do, but you just did the wrong thing. Yeah, but like it'll be like a case-by-case basis. So yeah, but yeah, you will need the justification to get the full credit on the true-false. Okay, so 10 true-false questions. Let's just run through these fast. Let V1, V2, V3 be 3 vectors in R3 if the span of V1, V2, V3 is a plane, then the vectors are necessarily linearly dependent.
For the wording on this one, is this saying that all 3 of them are linearly dependent on each other? Is it saying like two of them must be dependent of the 3?
It's just one of them can be written as a combination of the other 2.
Okay.
Yeah. Or at least one can be written at least one vector can be written as a combination of the rest. That's how you want to think of linear dependence. All right, so if you have 3 vectors in R3, but the span of the 3 vectors is just a plane, are the vectors dependent? Yes, right? Because what happens if they're linearly independent? What would the span be? R3. Yeah, all of R3, exactly. So this one is true. Okay, that was A. B, A is an m by n matrix. If m is greater than n, then the null space, so the kernel, that's what we call it in this class, then kernel of A must contain infinitely many vectors. Okay, so A is m by n, so this is the picture that I love to draw, right? Mn. And if m is greater than n, which means it's taller, right? So in order to, I guess, make that visual, right, there you go, then the kernel of A must contain infinitely many vectors. So what's the condition when the kernel of A contains infinitely many vectors? You have a free variable, right? Does this have to have a free variable?
No.
No, right? Because we can have something like that, right? So then what is this? True or false? It's false, right? Okay. What if we flip it on you? What if I said n was bigger than m? Then it's true, right? So that comes back to that linear independence problem that we talked about earlier, right? Where if you had a wide matrix and you're trying to show that they're linearly independent, right? Then you're definitely going to have some free variables at the end, right? And remember, showing linear independence is essentially finding the kernel of that coefficient matrix, right? Because if you think about the equation that we set up, it's something is equal to 0, and that's what the kernel is. Okay? C. If A and B are invertible, then if A and B are invertible, then A times B must be invertible. True or false? Yeah, this one's true, right? You had this on like a recitation homework. What? Anyone have an idea of the proof?
The determinant property.
Yeah, the determinant property, right? So if A and B are invertible, determinant of A and determinant of B are non-zero. So if you determinant of A times determinant of AB is equal to determinant of A times determinant of B, and so from there you'll get it. Yeah.
Use AB inverse equals B inverse A inverse.
AB inverse equals B inverse A inverse. Yeah, because B inverse exists, A inverse exists, so the thing exists. Yeah, that also works.
Wait, can you explain how using the determinant property works? Because if the determinant was 0, wouldn't that still be 0?
Yeah, but okay, so determinant of AB is equal to determinant of A times the determinant of B, right? But AB are invertible, right? So this is not 0, and this is not 0.
Okay.
Yeah. Yeah, so this would be like the justification we want to see on the true-false, right? Like literally that much right there is enough. All right, part D. Any n by n upper triangular matrix can be row reduced to the identity matrix. I'm just going to say to IN. All right, so any n by n upper triangular matrix can be row reduced to the identity matrix. Is this true or false? 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 True? True? False? 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 None of the above? Well, it's a true false, so it's one of them. It's false. Why is it false? Yeah, so you can have the n by n matrix be the 0 matrix, right? The 0 matrix is upper triangular. So this is false. counterexample 0 matrix is upper triangular.
Is that the only exception?
No, you can have something like this. Right, this is also upper triangular, right? As long as you don't have entries on the diagonal, like. But when you want to think of like counterexamples, just like always go to like the simplest thing you can think of. So like you would think of the identity matrix, and then you would think of like the 0 matrix, yeah.
Could you say that you have an upper triangular with determinants equal to 0 as also?
Yeah, I think, yeah, because upper triangular determinant equals 0, yeah. I mean, just go for the simplest thing that you can think of. Okay, E. Let's see. Okay, this one should be really easy. A linear system AX equals B with A n by n invertible has a unique solution. True or false? True, right? What's the unique solution? A inverse B, exactly. Okay, F. So I'm actually like writing out like justifications like that you'll need like if these were all like justify the true false. Okay, F. The null space of A m by n is a subspace of R m. True or false? One false. Yeah. Yeah, it's false. Okay, so this is like the picture that I love to draw in recitation. M by n, n by 1, m by 1, right? A x equals b, right? What is the null space? The null space is set of all x's such that ax is equal to 0, right? But what dimension is x? N by 1, right? So x is in Rn. So this is false. All right, x is in Rn. And yeah, so the null space, right? The definition of the null space is all vectors x such that ax is equal to 0, right? And so since A is an n by n matrix, you see that n has to be n by 1, right? So x has to be in Rn, not Rm. Okay, so keep that in mind. This picture, like, if you're stuck on one of these problems, just draw that picture out. I do it all the time, yeah.
So if Rn is smaller than Rn, does the vector in Rn, is it in Rn as well?
If n is less than m, yeah. So it's yes and no, because they're like infinite copies of so for example, in three-dimensional space, right? If I have a two-dimensional vector, there's infinite copies of this two-dimensional vector in that space. So, like, in that sense, it is in the dimensional space. I forget how the book treats it. I feel like the book treats it as if it isn't, because like it's not like a unique vector in the space. So, you won't have to worry about this on the exam, I think. All right. G. Let's see. If it is possible to express one of the vectors in a set S, if it is possible to express a vector in a set S as a linear combination of the others, then S is a linearly dependent set. True or false? This one's just straight up true. Yeah, this one doesn't have good justification for it. We'll just leave it like that. Yeah, it's by definition.
Is that the same for A?
For A?
With
Yeah, A is just with, it's just the span definition.
just the span?
Yeah. H. If each element of A n by n is doubled, then det A is also doubled. False, right? When is this? What is it actually equal to? Yeah, 2 to the n. That's not red. Right? You'll get det of 2a is equal to 2 to the n det A. So it's actually true if n is equal to 1, right? Yeah, I don't think this will make it up, because if you say true and you say true when n equals 1, you're technically correct. But I guess n by n is general, so. Okay, what are we on? We're on I. Okay, let's have AX equals B, and A is a 2 by 2 matrix. This system can have exactly 2 solutions. Yeah.
Wait, I have a question for the last one.
Sure.
Why is it 2 to the n and not 2 to the n?
Because A is square, right? So Mn is the same thing. Okay. AX equals B. Can the system have exactly 2 solutions? False, right? Can you ever have exactly 2 solutions? No, right? You can have 0, 1, or infinite. That's always your case. What if B were 0? What are the 2 cases you can get? 1 or infinite, right? Except that, so if you only have 1 solution, then the 1 solution is the 0 vector, right? Or you can have infinite solutions. Yeah, so this one's false. Okay, and then
For that, could you just do like a counterexample and show like a matrix which gives you a free variable?
you can literally just say a 2 by 2 like a system of equations can never have exactly 2 solutions. Like you can just literally state that. Yeah, so some of these like you won't see because there's just no good justification for them. Like some of these are just like, did you have the definition down? All right. J. If A n by n has a trivial null space or trivial kernel, sorry. There's a reason why we're calling it kernel instead of null space, and it's because once we move later on, the book starts calling the null space the kernel, but they're exactly the same thing. And for some reason, everyone just gets lost when we transition from null space to kernel, so we're just going to call it kernel the entire way. So, okay, so if A n by n has a trivial kernel, then for every vector B in Rn, there exists a unique solution to AX equals B. All right, so maybe some notation. This is there exists, and this is for every. True or false?
What is n to the n?
That's R to the n. Yeah, sorry, my handwriting's really bad. True? False? All right, what does having a trivial kernel mean? It's invertible, right? So do invertible matrices have a unique solution? Yeah, we literally did it above, right? So this is true. So trivial kernel means that, right, A is invertible. It really means rank A is equal to the number of columns. But since it's square, then that implies it's invertible. So X is equal to A inverse B is your unique solution. Okay? Any questions? All right, let's move on to problem 5. All right, problem 5. Let V be the subset of R4 defined as V is equal to x1, x2, x3, x4, given that x1 is equal to x3 and x2 is equal to x4. Is this a subspace? Of R4. All right, so this is your standard, is this a subspace type problem? Okay, so what are the conditions that we need to check? Yep, closed under addition, scalar multiplication. So closed under addition, and so what do we have? Well, now, okay, let's see how we do it. So take, all right, so we always need to take two general elements of the subspace, right? So in this case, x1 is equal to x3 and x2 is equal to x4. So what will they look like? They'll look like A, B, but then what does this third entry have to be? A, and then what's this last entry? B, right? Because that's how we get x1 equals x3 and x2 equals x4, and then we'll do like CD, CD. Right? So these are our general elements of our subspace, or of our subset in V. So this is in V. Okay, and then if you add them, A, B plus C, D, you get A plus C, B plus D, A plus C, B plus D. Right, and you see that this entry is equal to the first entry is equal to the third entry, and the second entry is equal to the fourth entry. So if you add them up, it's still in V. Okay. Closed under scalar mult. Same idea. We're going to take AB, right, in V. And then with the scalar mult stuff, we got to take K and R. And then, well, this is like, so now you want to show if K times AB is in V, but you literally just get KA, KB, KA, KB, which pretty clearly the first entry equals the third entry, and so on. So that works. So therefore, is a subspace. Okay? Yeah.
How do we check the zero vector here?
You don't need to.
Yeah, like,
Because if it's closed under addition, closed under scalar multiplication, zero vector automatically exists. I mean, if you have the zero vector is 0, 0, 0, 0. Yeah.
Are we gonna have to know the other 8 actions?
Probably not.
Okay.
Yeah, no. Like on your homework, you only ever need to do it for the last problem.
Okay.
So I think you can just check these two definitions. Okay, yeah. So the zero vector, you always check it if you have a hunch that it's not a subspace. Okay? You just literally see if 0 satisfies the condition. Right? You just find the zero vector of that subset and see if it satisfies the condition. But even if the zero vector is in the subset, that doesn't necessarily tll you it's a subspace. All right? Because you're going to have examples where the zero vector is in there, but it's not a subspace. Right? So, but closed under addition and closed under scalar multiplication automatically tell you that it's that zero vector's in there. So, all right, part. Let's see. This is part B, which is the following. Let's see. Oh, okay. So let P of R be the vector space consisting of all polynomials with real coefficients, and let V be the polynomials or be the subset of all polynomials of degree exactly 2 is V a subspace of PR. No, why is it not? Yeah, addition. Can anyone give me a counterexample? Exactly, x squared and minus x squared, right? So if I take x squared and minus x squared, then we see that x squared plus minus x squared is equal to 0, but 0 is not a polynomial of degree 2. Right, so the answer is no.
Is that true for all polynomials of an exact degree?
Yeah, it is. So if you ever see polynomials of exact degree, that's never a subspace. Okay, any questions? All right, problem 6. Okay, so a little background about problem 6. I actually wrote problem 6 on last year's first midterm, and it ended up being the hardest problem on the midterm. But I didn't write any problems on your midterm this semester, so you're okay. So this is the problem. Find a system of equations where the solution is given x1, x2, x3 is equal to 2 plus t, 1 minus 3t, and negative 3 plus 2t. Okay, any ideas? Yeah. You have to come up with that. All right, so you have to come up with A and you have to come up with B, but I gave you X. Yeah.
So isn't it just that you've got one free variable, so then at the top you've just got one column which will equal zeros, and then you do at the top that it's 2 plus 2, 0, z equals 0, and then you get 2 minus t, and you just make the system with one free variable?
Yeah, so that's one way to do it. So when we're talking about free variables, right, the t's are always equal to each other, right? So what we can do is we can write t is equal to some combination of like x1s and x2s, right? And then in that way we can get the coefficient matrix. what you're saying is you're saying that we have a well, so first of all, we won't have a column of zeros, we'll have a row of
A
zeros.
row of zeros. Yeah, so like you'll know that like one of the rows will be 0.
Yeah.
So then at the top, you know, like for the top one, it could be like 2, 0, -1 at the top, and that would give you.
But you're assuming the right-hand side is 0, I think.
Oh, and you're not allowed to do that.
Yeah, you're not allowed to do that because the right-hand side might not be 0.
Okay.
So, okay, let's see how we do this. So obviously we have a free variable, right? So let x1 be the free variable. Okay. Actually, I don't like how I'm looking at the professor's solutions. I don't like how you wrote it. So let's not do this. All right, this is what I'm thinking. So all right, so you got x1 is equal to 2 plus t, x2 is equal to 1 minus 3t, and x3 is equal to negative 3 plus 2t. So what I want to do then is I can solve for t and just plug that into the other equations, right? Because t is going to be the same across all three rows, all three equations I have written up there. So if I let t equal one of them, and then I can just plug them into the other two equations, then I have a system. So what am I talking about? So let's look at this first row, right? This is really t is equal to x1 minus 2. Right? So now what do I do? Well, from row 2, or from the second equation, I get x2 is equal to 1 minus 3 times x1 minus 2. Right? I plugged in t. This is t. Right? So now what is this equal to? This is x2 is equal to 1 minus 3x1 plus 6. So this is x2 is equal to 7 minus 3x1. But we want the x1s and the x2s like kind of on the same side, right? So now we get 3x1 plus x2 is equal to 7. So that's one of our rows of the system of equations, okay? And then from the third equation, how do you spell third? All right, what we'll get is now we get x3 is equal to negative 3 plus 2 times x1 minus 2, right? Remember, this is t. All right, so now you get x3 is equal to negative 3 plus 2x1 minus 4, right? Distributing that 2 in. So x3 is equal to negative 7 plus 2x1, and then moving everything over to one side, you get negative 2x1 plus x3 is equal to negative 7. All right, I got my two equations. All right, so now I just need to put them into a matrix, I guess. I mean, you could just circle those two. But essentially, what you'll get then is you'll get 3, 1, 0, 7, and then negative 2, 0, 1, negative 7. And if you actually try to solve this system, you'll get exactly what we presented. Although not entirely the same, because remember, this is a line, right? The solution is a line, so it might be shifted a little bit. But so this problem was a massive pain in the ass to grade because we had to check if everything was equal to that line if you were like shifted down. But that's correct. Any questions? All right, so this is one of those like you just have to like see it once to know how to do it. Like it's one of those types of problems. All right. Okay, problem 7. Last problem on this exam. Suppose A is a 2 by 3 matrix such that A times 1, 2, 3 is equal to U, and A times 1, 0, 1 is equal to V. All right, where U and V are in Rn. So first of all, what is the value of n? And then second of all, find x in Rn or R3 such that Ax is equal to 3u minus 2v. Okay? All right, so first part of the problem, what is the value of n? Two. All right, and again, it's this picture, 2 by 3, 3 by 1, 2 by 1, right? And then so u and v are in the output space, right? They're these guys, so they're in R2, so n equals 2. Okay, the second part, find x in R3 such that Ax is equal to 3u minus 2v. Any ideas on how to do this? It's not a trick. If something seems intuitive, it's actually correct here, yeah.
Substitute u equals a 1, 2, 3, and then a for v equals a 1, 0, 1, and then solve for, and then x goes away, a goes away.
Okay, yeah. So, right, you can do that. It's not that hard though. Yeah.
Multiply the first matrix by 3, the second by 2.
Yeah. So, all we really have to do, right, is the following. So your output, you want 3u minus 2v, right? So that means for our u input, we just need to multiply by 3. For our v input, we need to multiply by 2, and then we just need to subtract those inputs. Okay? Yeah.
I still understand how you got the value of that.
So a is 2 by 3, right? X is, so this is the ax equals b, right? X is 3 by 1.
Did you get the numbers, like the 1 and the 3?
Oh, I got the 1 and 3 mixed up. Yeah, but yeah, there you go. So x is 3 by 1, and then your output has to be 2 by 1, just by matrix multiplication, right? And then so you're asking where u and v are from, right? And u and v are 2-dimensional, so they're in R2.
Isn't it like n by n, so it's like 2 by 1?
If it's by 1, we just ignore the 1. All right, so it's like, right, in 3-dimensional space, if I give you a vector in 3-dimensional space, it's always going to be like a 3 by 1 vector, right? But we never say it's in 3 by 1 dimensional space, so we just kind of ignore that one. Okay, yeah. So part B, right? So essentially 3u plus minus 2v. X is going to equal 3 times this first input, which is 1, 2, 3, right? Minus 2 times the second input, which is 1, 0, 1. Why are these colors switching on me? And then, so that's going to be 3, 6, 9 minus 2, 0, 2, which is 1, 6, 7. Right, so if you multiplied A by 167, that's equal to 3u minus 2v. And the reason is because matrix multiplication is distributive, right? So A times 3, 1, 2, 3, minus 2 times 1, 0, 1 is equal to 3A, 1, 2, 3, minus 2A, 1, 0, 1. And then we know what this is. This is U, and this is V. So this is the check. Okay? Yeah.
Should we expect like a midterm more like this length than the practice one that from?
Yeah, because McGrath's practice midterm was like what? It was his midterm was a 50-minute exam last semester, and so you have 80 minutes, so it'll be longer. Although I think this exam was only 60 minutes, so it should be around like 7 questions ish. Yeah.
Can we multiply the vector by 3 and then the other one by 2? And solve, like not really solve, but like simplify it.
Yeah, that's what I'm doing here, right?
Okay.
Yeah, I mean I just took 167 and I just wrote it out like that. All right, there's actually a part B to this problem, so hold on tight. Part B is to find a 2x3 matrix A such that the null space or the kernel of A is equal to the span of 1, 2, 3. Okay? So what does that mean? Well, that means that in the kernel of my matrix, there's like this vector will zero out, right? A times, that's a really weird color to be using. A times 1, 2, 3 is going to equal what? 0. Okay, because 1, 2, 3 is in the kernel of A, right? So the span of 1, 2, 3 just means every other like linear combination of 1, 2, 3, which are just scalar multiples of itself, right? So any scalar multiple of 1, 2, 3 is in the kernel, which means that itself is in the kernel. And so in this case, now we need A times 1, 2, 3 is equal to 0. So what can we do? Well, you kind of just have to let A be like A, B, C, D, E, F, right? And then multiply that by 1, 2, 3, and you get the 0 vector. Okay? And what we kind of have to do is that we kind of just have to eyeball this. So you have A plus 2B plus 3C is equal to 0. You got D plus 2E plus 3F is equal to 0. And you just need to come up with some A, B, C, D, E, F that satisfies this equation. Like literally any A, B, C, D, E, F works. All right? Yeah.
A, B, C, and D, E, F, they can't be scalar multiples, right? Or else you'd have a bigger.
Yes, exactly. So that's the other thing. So if you like choose A, B, C, and D, E, F, so if you choose A, B, C, you have to make sure that D, E, F is an exact scalar multiple of it, because then what would the span be? It'd be a plane, right? Because you'd have, so if D, E, F were a scalar multiple of A, B, C, when we row reduce it, we get pivot free, right? So we have 2 free variables, okay? And that means we would have 2 vectors in our span. Okay? So that's actually technically a little bit ahead, but it's the correct thinking. So what we want is we want pivot free, which means then DEF can't be a scalar multiple of ABC. So one way we can do this is then let, I don't know, A equal 0, B equal -3, and C equal 2. All right? And so that means I can't do DEF. Like I can't have like +3 and -2 here. Like this is not allowed. Okay? So instead we'll do D equals -3, C equals E equals 0, and F equals 1. All right, and so now my matrix A, 0, -3, 2, -3, 0, 1 has a kernel that's spanned by just that vector 1, 2, 3. All right. So yeah, the problem was literally like come up with anything. So, I mean, the zero matrix doesn't work because everything is in the kernel of the zero matrix, or like every three-dimensional vector is in the kernel. Okay, any questions? On this one, that was the exam. So that was the entire exam. I think the average was like about 80% on this exam. Yeah.
Will there be differential equations on the exam or just?
Yeah, you should expect those. Those are fair game. Yeah, differential equations are fair game. So,
Will
yeah.
mapping as well be like with the airport question, where it was like the airport goes, like how many paths there are?
You should know how to like set up those kinds of matrices, but you don't actually have to like explicitly calculate them. I think that was like the idea.
Okay.
So, I mean, you should like have that. You should know what that is about. The only thing I'm allowed to say that's like explicitly not on the exam is the linear regression, line of best fit stuff. Like that's like the only thing that's like not on the exam that I can say. Anything else is fair game. Yeah. No, I have them. I mean, so they're in the 240 notebook that I have linked on my website, so we can talk about that. Yeah, so this stuff is there. All right. Let's move on to another midterm. Okay. So now this is Palvannan, midterm 1, fall 2017, 2018. Okay, so all right, let's do this. 1A. Let B equal 2005. What is B to the 17? Yeah. All right, so if you have a diagonal matrix and you start raising it to powers, it's just 2 to the 17 and 5 to the 17. Yeah. No. I mean, this is like 100% correct, right? 2 to the 17 is the entry in there. Yeah. Yep, because if you have something like 1101 raised to the n, this is actually like 1n01. That's actually something really cool. So yeah, if it's diagonal, then if you raise it to the power. All right, any other questions on this one? Part B, find the inverse. I mean, a lot of these are like, I mean, they can only test you on so many things. 2, -1, -1, 1. Okay, so let's use the determinant shortcut. So determinant of A is equal to 1. So A inverse is equal to 1 over the determinant of A times 1, 2, 1, 1, right? So you flip the main diagonal and then you take the negative on the off diagonal. So this only works for a 2 by 2, and this is equal to 1 over 1 times this. So that should be your matrix.
Isn't the determinant 2 minus 2 though?
No,
Oh,
it's
2
2
minus
minus
1.
1. Okay. Part C. Let's C equal A, B, A inverse. Compute C to the 17. We actually had a problem like this, right, on the homework? Yeah, so it's A, B to the 17th, C to the 17th is equal to A, B to the 17th, A inverse. So yeah, a lot of things on the homework's going to come back. So A, B to the 17th, A inverse, and then, so you actually have to like compute this. You found what A was, well, they gave you what A is, right? 2, -1, -1, 1, B to the 17th is all this, and then A inverse is that. Okay, so now this is just like matrix multiplication, and you should get the following: 2 to the 18th minus 5 to the 17th, negative 2 to the 17th plus 5 to the 17th, 2 to the 18th minus 2 times 5 to the 17th, and then negative 2 to the 17th plus 2 times 5 to the 17th. Yeah?
Why is only b to the 17th?
Write it out. So let's say c squared. That's AB, A inverse, AB, A inverse, right? What happens? Well, these two cancel, right? A inverse and A get the identity matrix. So now what you have left is AB squared, A inverse, right? Then what is C cubed? Well, C cubed is equal to C squared times C, which is AB squared, A inverse, times AB, A inverse, right? What happens to the A inverse and A? Well, they cancel out. Now C cubed is AB cubed, A inverse, and from here you should be able to recognize the pattern. Okay. It's on your homework too. You showed it. I think you proved it on your homework, right? For some general n. Okay. Problem is, okay, so that's C. All right. Problem 2. Is, okay, let D equal 1, 0, -1, 2, 1, -3, 1, 2, -3. B is equal to B1, B2, B3. And E is equal to 1, 2, 1, 0, 1, 2, -1, -3, -3, B1, B2, B3. Okay, so they essentially give you like a coefficient matrix, the right-hand side, and then they make you like solve the system. Okay, so part A is to compute the echelon form of E. So this is really row echelon form, right? So we just have to reduce E down to the, we want to reduce E down to echelon form. So how do we do that? Well, row operations. Okay. So now you get 1, 2, 1, 0, 1, 2, 0. I'm adding row 3 to row 2. So 0, -1, -2. B1, B2, and so I'm adding row 3. Sorry, I'm adding row 3 to row 1. So this is B3 plus B1, right? And then 1, 2, 1, 0, 1, 2, 0, 0, 0, B1, B2, and then I added row 3 to row 2. Okay, any questions? All right, so now part B is the following. What is the algebraic equation that describes, well, equations that describe the vector space spanned by the columns of D in R3. I think we can leave those. That's a span. Okay, so the columns of D, right here, this is D, they span some vector space in R3 or some subspace of R3, right? And what is the subspace that they span?
C1 times 1, 0, negative 1 times plus C2 times 2, 1, negative 3.
Yeah, okay. So yeah, they do span. So those two vectors are in the span, but we want the algebraic equation for the span. Yeah.
Is it the plane B1 plus B2 plus B3 equals?
Yeah, exactly, right? So in order to span something, right, you must have a solution to your system of equations with your columns, right? And so in order to have a consistent system, this guy here needs to be 0. Okay? So this answer then is B1 plus B2 plus B3 is equal to 0. Or if you want to like interpret it in R3, you can write x plus y plus z is equal to 0.
What is the fourth word in the question?
Algebraic, yeah.
Sorry.
You're good. My handwriting's not very good, so. Yeah.
Could you just explain that again? Why?
Yeah, so what are we doing here? We're essentially we're solving for some x vector here, right? And essentially we have some system which is D times some, well, let's not even call it x vector, let's call it some c vector is equal to b, right? Because that's why we have D and B put in this augmented system, okay? So what is C? Well, if C is equal to C1, C2, C3, right, our system of equations is essentially C1 times the first column, 1, 0, negative 1, plus C2 times 2, 1, negative 3, plus C3 times 1, 2, negative 3. Okay, so that's the system that we're essentially solving. And this is equal to some B1, B2, B3, right? And we want this system to have a solution. All right, so what happens? Well, when we row reduce this system, right, we literally put this system into this matrix right here, right, and we row reduce it. Well, when does the system have a solution? Well, it has a solution if B3 plus B1 plus B2 is equal to 0, right? So that means the three column vectors that we have, their linear combinations have to be in this plane. Yeah.
If that wasn't the solution, say like B3 plus B1 plus B2 did not equal 0, then it only would span R2, right?
Well, B1 plus B2 plus B3 is R2, right? It's a plane, right? So a plane is a two-dimensional object, and you're in a three-dimensional space, right? If that were non-zero, what would happen is it means that, because remember, B1, B2, B3 is just a random vector you give me, right? So if that last entry is not 0, that just means that whatever vector you gave me cannot be written as a linear combination of the columns. That's all that means. Right now, we're showing that it does span R2. Any other questions on this one?
How would you do for the rows?
For the rows?
Like,
Well, I mean, we're not worrying about we're not really worrying about the span of the rows. And in general, we actually don't really care about the rows of a matrix, because you can always think about it this way. If we wanted to care about the rows of the matrix, take the transpose. Now they're the columns of the matrix. Yeah, so we don't really care about the rows. Yeah.
So the vector space span means that like the determinant can equal 0, or sorry.
The vector space.
Like what's the last question? Like why is the condition that like 0 equals 0?
Because so right, what I'm saying is, right, B is B1, B2, B3, right? It's just this arbitrary three-dimensional vector I'm giving you, right? I'm trying to write it as a linear combination of the columns of D. Okay? So when I set up my system of equations, C1 plus 1, 0, negative 1, plus C2 times 2, 1, negative 3, plus C3 times 1, 2, negative 3, I want that to equal B1, B2, B3, right? So I'm saying that some linear combination of my columns has to be able to hit this vector, right? And so what's the definition of span? The definition of span is every possible linear combination of a set of vectors. Okay? So I have to consider every possible linear combination of my column vectors, and that happens to be this plane, which is b1 plus b2 plus b3 equals 0. Yeah.
So we wouldn't also have to write down the other two? Like you know, I said b3 plus b1 plus b2
Yeah.
equals 0. You don't have to do that for the other.
No. Yeah, the other two rows, like, we don't talk about that because, like, you don't need to, because the only place where the system fails to have a solution is if that last entry is not 0. Okay? Any other questions? All right, let's move on to 3. 3 okay, let V is the set of continuous functions f that has an input in R and has an output in R. All right, so this just means this is your input vector space, and this is your output vector space. Okay, and f is just the name of an element or a function. Okay, V is a set of continuous functions that does this. Assume that V is a vector space over R. Okay, so we know that V is a vector space. Consider the two following subspaces or subsets. Subset 1 is equal to y of x in V such that y double prime plus y cubed is equal to 0. And the second one is S2 is equal to y in V such that y double prime plus 3xy is equal to 0. Okay. One of these is a subspace. Identify which one it is and prove that it is a subspace. And then for the other one, we just don't talk about it. All right? So 1 is a subspace and prove it. All right, any hunch on which one of these is a vector space? The second one. Why not the first one? The y cubed term, whenever you have like that y cubed, it kind of messes with things. So let's prove B. Yeah, the y cubed really messes with closure under addition. So now what you have is, okay, so prove B, close under addition. So it's the following. Take, what are my general elements I want to take? Yeah, let's call them y1 and y2. Right? You can think of them of x if you want to. You don't have to include that of x inside S2. All right? I want to show that y1 plus y2 is inside S2. Okay, so how do we do that? Well, we plug in y1 plus y2 into the condition. Right? So now you get y1 plus y2 double prime plus 3x times y1 plus y2. So notice that x is just an x, right? It doesn't change. Okay, and then is this equal to 0? Okay, double derivative distributes over addition. y1 double prime plus y2 double prime. And then here you get plus 3xy1 plus 3y2. Rearrange the terms, y1 double prime plus 3xy1 plus y2 double prime plus 3, oops, I dropped an x, 3xy2. All right, what is this first term? 0. What is this second term? 0. And my night light is coming on. Okay, so now this is 0 plus 0, so that's equal to 0. All right, so it's closed on our addition. That's good, because that's what we wanted to show, right? Close on our scalar multiplication. Same idea. Now we take y in S2, k and r. All right, and we want to show that ky double prime plus 3x times ky is equal to 0. So how do we do this? Well, factor out the k. Y double prime plus 3xy. And that's just equal to k times 0, which is equal to 0. A lot of the times with scalar multiplication, the check is literally factor out the k and you're done. Okay. Any questions on this? Yeah.
If we're given a question like this on the exam, are we allowed to prove the other is not a subspace by half?
No. So this one says you must prove that one of them is, you must show that the one that is a subspace is. That was like the wording on the exam, so yeah.
But isn't that equivalent to proving that the other is not?
Well, they wanted you to explicitly show that the one that is a subspace is a subspace, so there's no getting around it, yeah.
How are they looking at like the Y cube on it?
Because when you want to do stuff closed under addition, right? If you'd have like y1 plus y2 double prime, and then you'd have to add y1 plus y2 cubed, right? Yeah, but then you get like the y1 times y2 terms in there, right? You'll get like y1 squared times y2, y1 times y2 squared, right? And then because like you don't have any of those anywhere else, you can't assume that those are 0. Yeah. Also, this one's considered linear in y. Okay. Even though there's like a 3x, x is essentially just like a constant, right? In terms of like y. So anytime you see something like linear that looks linear, that's probably going to be the one that's the subspace. Okay, problem 4. All right, here you have a few information. So number 4, suppose you have f, which is 3 by 3, satisfying f of x is equal to 1, 1, 1. Or f of x equals 1, 1, 1 has no solutions, but f x is equal to 1, 2, 3 is consistent. Then does fx equal 1, 2, 3 have a unique solution or infinitely many solutions? Okay, so f times x equals 1, 1, 1 has no solutions. F of x equals 1, 2, 3 is consistent. So then does that one have no solution or infinitely many solutions? Yeah, infinitely. Why?
You have to have, if you have no solution, the only way you can have that is a 0 row equals a non-zero constant.
Right.
So that means it's not invertible.
Okay.
So that means invertibility implies unique solution.
Exactly.
So I think the opposite.
Okay, yeah, so that's one way to think about it. You can think of invertibility. Right, so f of x equals 1, 1, 1. No solution means f is not invertible, right? Does everyone agree? F is square, right? So if I can find something, because if f were invertible, then every vector, every b vector that you give me would have a unique solution, right? X is equal to a inverse b. All right, so we've hammered, I think, that equation in like 3 or 4 times now. So that has no solution. So f is not invertible. What does that tell me? This tells me that f, the rank of f is what? Less than 3. Okay? So if f of x equals 1, 2, 3 has a solution, then rank of f is going to be equal to the rank of the augmented matrix f, right, with the solutions added together. So if there's a solution here, that means rank of f is equal to the rank of the augmented matrix. But what is that equal to? That has to be less than 3, right, because the rank of f is less than 3. And based on that one table in recitation that I covered, what does rank of f equaling the augmented matrix being less than the number of columns tell us? There's a free variable, there's infinite solutions. Right, and I should note that 3 is the number of columns. So the rank of f is less than the rank of the number of columns, so there has to be infinite solutions. Any questions? Okay. Number 5 is the last problem on this midterm. Yeah.
Can you explain more the third one?
The third.
So if f times x equals 1, 2, 3.
Right. So that's this guy, right? So you know it has a solution. Then when you write this augmented matrix, then you know that this last row, like, has to be 0. Well, essentially, right? This is f, and the entire thing is f augmented, right? So if the rank of f augmented is greater than the rank of f, what does that mean? That means you have like something like that going on, right? But if the rank of f is equal to the rank of f augmented, then you won't have this case, right? And then, so that means, so when this is equal, there's a solution, right? But you need the rank to equal the number of columns, because otherwise you're going to have a free variable, all right? So that's how we know. Let's leave that in there. Why not? That's how we know that like it has infinite solutions. Yeah. All right, and I like talk about this in one of the recitations, right? Also on like the definition sheet, there's like a table that has essentially this on there, so it's out there. Okay, and we do expect you to know it. All right, number 5. True, false, no justification. 3 of them. A. Every vector space has a unique spanning set. False, right? Why? Well, just think of like R2, right? If my fingers are like this, that's a spanning set. And then if I like rotate this vector over, that's still a spanning set, right? So this one's false.
Does that mean that could this question be interpreted that each individual vector space has a unique spanning set relative to all other vector spaces?
No. The way you want, so I think what you want to say is each vector space has a unique dimension.
Yeah.
And that's true.
Okay.
Right? So every spanning set is going to have the same number of vectors.
Okay.
Or every base, well, was this basis or spanning set? Because if it said basis, so let's just talk about basis then, right? Every basis for a vector space has the same number of vectors. Right? So for like R3, right, for 3-dimensional space, I'm going to need 3 linearly independent vectors no matter what.
Okay.
Right? If you give me a 4th vector, it's automatically going to be a linear combination of the previous 3.
Okay.
And it's also why we don't. That's also why we don't include 0 as like a vector in our span, because it's, like you have 3 linearly independent vectors, you're going to be able to get 0. So yeah.
Does a vector space have an infinite number of spans?
Yeah, so spanning sets is a spanning set just means any set that spans the vector space. So it's not even a basis, right? Because a basis is like the minimum number of vectors you need, right? So a spanning set, like I could have given you like 7 vectors in R2, like okay, whatever. But even then, even if this said basis, it'd still be false, right? Because again, that's with like I have these 2 vectors, but I could have also given you these 2 vectors, which would have spanned R2. So yeah, so spanning set. So even if that question asked basis, it'd still be a false.
So based off that, can you define a spanning set as either a basis or a basis plus redundant vector?
Yeah, exactly. That's what it is. Of a vector space, yes.
Of a vector.
Yeah, of a vector space, yes. Yeah.
When you're proving like if if the differential equation is a subspace, can you say it's like a subspace of the vector space of all functions?
Yeah.
So that's always like the go-to.
Yeah, that's the go-to for differential equations. Yeah, all continuous functions, or continuously, however many times differentiable you need it to be. Because sometimes if you differentiate a function, it stops being continuous, right? And then you can't differentiate the derivative, right? So if I'm asking you for like y double prime, but y prime is not continuous, then you can't take a derivative, right? So you just make the relevant assumptions you need. Yeah. Okay. Part number 2, I'm not even going to do, because we did already. If A, B are invertible 2x2 matrices, then A times B is an invertible 2x2 matrix. True. Yeah, we did it. Okay, so C, the set of even polynomials P of X in P and R is a subspace of P and R. So what does even mean? Even means f of x is equal to f of negative x. True or false? For C. For those of you in my recitation, I actually did C in a Friday session.
Is it false because under addition you could get the 0? It's like for if you had like evens, it's like what we proved before.
Not quite. So C is true. All right, and let's show it.
Does even imply also even powers?
No. Actually, it does. Even does imply even powers. Yeah, you can think of it that way, but let's just show it and we'll see, because you don't even actually have to write out the powers in this case. So close under addition. All right, we'll take P1 of x and P2 of x. All right, this is a trash name for a set. So we're just going to define this as S. And then we'll say these are in S. All right, so what does this mean? We know that P1 of x is equal to P1 of negative x, and we know that P2 of x is equal to P2 of negative x, right? So that's what P1 and P2 being even imply. And then, so you want to show that P1 plus P2 of x is equal to P1 plus P2 of negative x. All right, so what I get is I get P1 of x plus P2 of x is equal to P1 plus P2 of x. All right, so you can just do this with functions. Well, okay. I started the wrong way. So P1 plus P2 of x is equal to P1 of x plus P2 of x. All right, we did backwards, but that's fine. All right, but what is P1 of x equal to? P1 of negative x. Right, and what is P2 of x equal to? P2 of negative x. Right, and then we just combine these now. Okay. So this is even, right? Because P1 plus P2 is just a function. And then x and negative x are the same thing. Okay, and then close under scale of multiplication. You just take that k out and you're done. So P1, take P of x and s, k and r. And then you get kp of x is equal to kp of negative x, I guess. Yeah.
If it was odd, would it not be?
No, odd also works. So I actually encourage you to go home and try that. It also works. Odd works. Okay. So this one's true. Okay. Let's see. Okay. These are multiple choice questions. So let A be n by n. Consider the following two solutions. Let's just treat these as true. Let's just treat these as true or false. So they're really just true or false questions, but they're multiple choice questions. No. This is Palvannan still. So statement A is the following. So I guess this is like part B, and then we'll just call this like 1. The reduced row echelon form of A squared is equal to the identity matrix. Then the reduced row echelon form of A is guaranteed to be the identity matrix. And then the second one is if RREF of A is equal to the identity matrix, then RREF of A squared is equal to the identity matrix. Okay, so first one, is it true or false? It's true. Why? 6.
Oh, okay.
Yeah, yeah.
6.
Yeah.
Thanks. This is multiplication of matrices with full rank.
Yeah, exactly. So if you multiply matrices of full rank, it'll stay full rank? Yes, it will. All right. So, so here's the thing, right? You know A squared is full rank, right? And you know that, remember this, rank AB is less than or equal to the minimum of rank A and rank B. Right? So if A were not full rank, then A squared could never be full rank.
Can you show with determinant, so it's the determinant of A is non-zero, then A squared.
Yeah, that also works too. All right, so you can use this, you can use the rank argument, or you can use the determinant argument. So the first one's true. What about the second one? Why? Same argument. Yeah, so the second one's also true. And it's because full rank matrices multiplied. Product of two full rank matrices is full rank. Square matrices. All right, and another way to think about it, this is just extra, but if you have two full rank matrices, right, you can never have a column in the null space of the other matrix. Right, because remember, you're doing like dot products of rows and columns, right? So if it's full rank, the kernel is trivial, And so you can never have like a column be in the kernel of your first matrix in order to get the zeros. We'll hammer that in a little bit later, but you can that's something you can think about now. All right, last question on this exam. Yeah, okay, let's just not do the last problem of this exam. It's not very good. It's just 1 point with like some like, you just need to check if some vectors are in spans. It's not a very good question. All right, so we didn't get to McGrath's midterm. That's fine. If you have any questions on it, just post them in Piazza. So yeah, I'll upload this. If you have any questions, feel free to post on Piazza, shoot me an email. The key to what? There isn't. If you have any questions, just post it on Piazza. Like, yeah. Yeah, go for it.
So when it says like a basis spans a vector space, does that mean like the basis is the combinations of linear combinations that compose that vector space?
Yeah, so the linear combination of those basis vectors
Is
like
span. Like when you have
is span, right? So every linear combination of the basis vectors is the span, and
you want to prove that that is in that vector space with the statement of like basis B spans vector space like V.
okay.
If you want to prove that, then you're
Right.
proving that it's combinations of linear, or it's the set of linear combinations.
Right.
Okay.
Can hit every general element of your vector space.
Yeah.
Yeah.
Okay. And then in order to prove that, you need to say that the dimensions are the same between the basis.
Right. If the number of elements in your basis
Yeah.
equal the dimension of your vector space,
then it proves both that it's linearly independent.
no, then you have to prove it's linearly independent.
And then that qualifies it to be
Span. Yeah, exactly.
Can it be vice versa?
Yeah, if you show that they span, then they're linearly independent. Yeah, but it's easier to show linear independence. Yeah, you want to come upstairs with me when we're done here? Yeah.
I have a quick question.
Yeah.
I noticed like